Formal verification is not just a buzzword, it is a game changer in the world of engineering and technology. By leveraging mathematical techniques to ensure the correctness of critical systems, formal verification brings a level of assurance and trust that is invaluable in today's complex and interconnected world. So, whether you're a seasoned engineer or a curious enthusiast, dive deeper into the realm of formal verification and discover the endless possibilities it holds. Thank you for joining me on this journey to make formal accessible to everyone. Today, we will be discussing a key factor that makes formal verification difficult: the complexity of designs. Throughout this video, we will cover various techniques that you can use to address complexity. By implementing these techniques, you will be on your way to become a formal verification expert. Be sure to watch the full video to kick off your journey towards mastering formal verification. Thank you for watching. There are a number of ways that you can use to reduce complexity of your designs in formal. I am dividing them into three broad categories: basic, intermediate, and advanced. In the last three videos, we discussed certain basic techniques: parameter reduction, cut points, black boxing, the use of symbolic variables, and over constraining. In this session, we are diving into the intermediate complexity reduction techniques. I will be explaining the concept of case splitting and how you can implement them in your SV files with some example codes so that you can get started with your work as soon as you finish the video. Let's consider a design that does various operations on an incoming data. This is a sequential design with a buffer in the beginning. The buffer module that you see on the left hand side stores the incoming requests into the design with then the actual data transformer blocks. The request that comes into the request buffer has three fields. One is the data input, the actual data itself, and second is the data invalid, which says whether the data is valid or not, and the third input is the request type. And the second block, the data transformer, picks up these requests one by one and then does various data transformation operations. These operations can be addition, subtraction, XOR, or inversion in this case. To verify this design, we can write a single check that will ensure that the data coming out of the data transform block is the one that is expected as per the data which is coming into the request buffer based on the request type. So this is a bigger check that covers all the cases, all the four different type of data types: addition, subtraction, XORing, and inversion. For obvious reasons, this proof will take longer or can take longer based on the design size. Case splitting can come into play here. It can help split the check into different multiple ones and then help you achieve faster proofs. So what is case splitting? It is simply a method of splitting the check into multiple ones based on different cases that the check covers. Case splitting can be applied to designs or blocks that is different modes of operation. An example can be an ALU, which can do different operations like addition, subtraction, etc., like the one we are seeing here. How can we do case splitting? We just need to modify the check, as I will show you in the next slide, based on different cases or modes of operation that the main check covers. An important thing to note here is that we're not adding any extra assumptions, unlike the case of over constraining, where we would add an over constraint, which is essentially an assumption, into the tickle. That will limit the scope of the entire tickle, entire check itself. So everything is good there. So what are some common mistakes that people make while doing case splitting? The very common one is missing a case itself. If you split the check into n number of checks and you miss a case and you sign off the design without ensuring that if you covered all the cases, then that can lead to missing bugs. So how can we fix this issue? A simple fix is to add an assertion that says that at any point in time, at least one of the cases that you're covering should be true. Let's see how we can implement it. Without case splitting, you have one property, the one you see in the middle. The property has a field called data out FE model. It is simply it's generated by the formal verification model that you should be writing. It is ensuring It is the data out that is expected based on the data in that's being checked. With case split, you will have the properties that you see on the extreme right. You'll be splitting the main check into 4 checks based on the request type. This generates 4 checks obviously. And after that, there will be an additional check at the end that says that the request type can only be any of these 4 types or has to be any of these 4 types at any point in time whenever a data input is valid. That's all about case splitting. Now you know how to implement case splitting. If you're working on a design that has different modes of operation like we just saw, why not give case split a try? I'm eager to know how case split improves the proof times in your checks. Stay tuned for more complexity reduction techniques. I'll be sharing different abstraction techniques in the next video. And after that, we have more exciting videos in the subsequent sessions. Make sure to subscribe to our channel so that you never miss an update. Stay tuned for the next video where we will cover another formal verification topic. See you next time. Bye.